Thank you all for joining and for accepting this invitation for this talk. This talk is a continuation of the Sophia School that happened last month. There were many talks and they're all online. I will put the link in the chat. But one thing that was missing there was a description on how to analyze forecast images. So that's why we called in James Radomski from Sophia. He's a scientist at Sophia. Has been there for almost 10 years, I believe, mostly taking care of forecasts. So he's forecast instrument scientist, especially on the pipeline side of things. Before that, he was working at Gemini. So James, go ahead whenever you want to start.
All right, thank you very much. So today I'll be talking about signal, noise, and artifacts in forecast images. I'll be primarily focusing on imaging, but of course, these artifacts and noise can also affect spectroscopy, although I won't necessarily be going into depth in that. So, first, an overview. I'm not going to go over issues in the data handbook. You can go to the Sophia Science page and go to Data Analyst and download the PDF of the handbook. And that discusses a lot of issues with the pipeline, how data is reduced, issues like droop and jail bar, how it's accounted for and stuff. So I don't think there's a need to go over that. I will talk a little bit about the signal noise and site updates as far as how to calculate your signal noise and U-spot now. And then I will discuss QA, basically how I do it, where to find the information about the comments and stuff that I report and discuss regarding the data, and data issues that we've had past, present, and possibly future. Feel free to ask any questions during or after this talk, and if you have any follow-up questions, just hit the help desk, and it will eventually come to me or somebody else, and we can answer those for you. So to start off with is a big issue with signal and noise in general, and how you calculate it in sites. Now, emails have been already sent out, I believe, by Nicole to all the guest observers and such. So, is we've had a change of time calculation and U-spot in site. So now we're using exposure time instead of totin to calculate when a program is done. The difference is basically in how one defines source time. Some people define source time, like I said in the image below, where you have 4 frames, you have one node, chop on the source, chop off the source, on the source, and off the source. And so sometimes people define that as only on source images, it's only when there's actually data on the array of your object. Other people define it though is when it's the total of both the data and the off source, because you have to chop or you won't see anything. So that might have led to some of the confusion and stuff. So now this factor of 2, which only affects NMC data, it doesn't affect C2 and C2. But essentially, it's taking you twice as long now if you put in the same times from before in site and U-spot to do the same observation to get the same signal noise. Now, we are in the background limited regime, so even if you got half the data, you're getting 70% plus signal noise from previous observations. Possibly more, because we always tend to observe slightly more than the time you requested, just to make sure. So this has been fully implemented for cycle 10, and so all your cycle 10 proposals will have this all calculated properly. Cycle 9, we kind of retroactively try to adjust this for programs, depending on how important it was. So for some programs, for example, you're looking at bright sources, you're getting signal noise of several hundred in a few minutes. There is no reason to adjust the exposure times. However, on other faint sources and stuff, sometimes it was worthwhile to add some more time in, if we could, and extend these legs to try to reach the signal noise originally asked for. So this also goes into a larger factor for 6.4 micron observations and the Geo 6.3 micron GRISM. This actually is a separate effect, and this has got to do with the calculation of how FORCAST calculates the background and properly times out the frame times and chop cycles and stuff. So, and we found an error in this filtering GRISM and stuff, that the way it calculates the background sometimes is very inefficient. And so the parameters it defines can be very inefficient, much worse than even 2 times as much. So those observations may be affected more. We are looking into a fix for that. And if you have any specific programs or issues with the programs, feel free to contact your contact scientist and we can follow up on that. So I just wanted to talk about that real quick. Next, let's go over data qual. This is how you evaluate your data. This is a keyword in all the files and such. So there's essentially three things you should know by now. Nominal is, it's fine. This is the most common. Most data we get is nominal. There's no problems, no issues. It's all fine, goes in the archive perfectly. The next is usable. Usable is defined is kind of a large definition because there's some issue that affects the quality of the data, but there's a large range. Sometimes it's a very minor issue, but it's just that the quality of data doesn't quite fit what we should be. And it can be dependent on your program and what you require. But though we don't define it as usable by what you required for your science, but what the ideal scenario is for archival science. So for example, if all you wanted was a flux estimate of a source, maybe you don't care about the image quality being a little off. But if the image quality is a little bit off, I will mark the data as usable. So you may be fine, it may be nominal to you, but to somebody else in the archive may realize that the full width max or the elongation is much worse than what we normally expect in nominal conditions. Now this can go from something minor to something much major where the data is really rough, but is at least somewhat useful. So perhaps it's only useful for applying to time again. So you can get like a rough 30, 40% chance of the flux because there's clouds and issues and stuff, but at least it's some useful in some scientific way. So, and that is mostly rare, though it occasionally happens. Nominal may or may not have comments attached to it because if the data is fine, there's not much to say. Usable will always have a comment associated with the data telling you why it's usable in the first place. Fail is something that's basically data not useful in any possible way and is usually not archived at all. This is just data where it's like telescope went into local and we looked at the back of the cavity or something like that, or the noise completely dominates the array or something. So it's completely useless. We don't even archive it. It rarely happens and stuff. So now there's a difference. Some files do have some issues, and I do exclude it from the final coad. This could be just some turbulence cause some image quality issue and stuff. And so this can happen somewhat common, but it's a small effect. For example, if you're observing like 10 files, maybe one of them I found the quality is not good. So you'll still have the raw data, but I'll exclude it from the final coad because it adds nothing. And since the background regime is the square root of time, one file out of 10 is almost no effect on the signal noise. In fact, generally I exclude files to improve the signal noise. So this is an example of a QA sheet. So this is how I do quality analysis flight by flight, group by group. This is flight 261 from all the way back in 2015 up here. As you can see, this lists the object data, the data qual, and the GI comments and team comments. Team comments is just local stuff between us that we discussed, doesn't go into the files. They're just little comments to myself or the other people of the team. GI comments go into the files at the bottom of the files in the headers. It's also in URSA. You can click on it, get the QA comments and such. So, and it also goes in the email out to you for your program. So you can see here, most of the data is nominal. I made a little note where the cal difference is slightly higher than normal. It's about 12%, it's about 10%. So that was for the calibration scientist to look at. Here we have an example right here, telescope system crashed at the end of previous flight leg, some initial issues setting up and stuff. So data was nominal, but I figured it was worth reporting what was occurring at the time. In this file, some minor turbulence were reported in file 251, but when I looked at it, I saw no issues, so this is all nominal. If it was bad, I may exclude that one file, in which case I would say so. Any files I work on, I usually tag as manual, and I make some adjustments and stuff. So this one showed some vignetting, and I made a note of that. So this is kind of what I go through.
Can I interrupt you for a second?
Sure.
Data qual and GI comments, those end up in the FITS file in the headers, right?
Yes.
And they're under a key header data qual, and the GI comments, I imagine, are what is called QA comments at the end of the history keyword?
Yes. Yes,
Okay,
if you scroll to the bottom of the FITS file, that's where will be the GI comments, and I'll show that in a moment.
Okay, thank you.
So this is just an example of a sheet I typically go through flight by flight, looking at all the groups of the data, every single file, and making a comment and such. So, and here we talk about QA comments. They're by group observations. They're in the email sent to you. They're in URSA under quality assessment. If you look in URSA and you click on quality assessment, it will have the comment for that group. This is applied to all the files in that group. So it's written into FITS header for each file in that group. It's also at the bottom of the FITS headers right here. We see data qual. You can see where it was updated, who updated it, when I updated it. And in this case, this was just a note, this was an acquisition image, not a normal science image, and that there are some issues that caused the loss of this Vesta leg and such. So, so these are very important to look into this because this will tell you what's going on with your data. So, and especially if you're looking at older data. Now, one thing to look at for major issues, now these are all in the comments like that, but by cycle and stuff, if you go to the URSA web page and scroll down to the bottom, the main Sophia web page, you'll have known data product issues. This lists all the major issues for a series and such, or by multiple series and such. It's especially good for old data. The older data has more issues than the newer data as we fix stuff. Occasionally there's a one-off like OC6J, which had a problem with the window distorted heavily. These are updated pretty regularly right after a series is finished and reports major issues. So like I said, OC1B, we had some smearing because the chop settle was wrong and such. So you can just look at this sheet and just know of overall major issues affecting cycle. And this is especially good looking for old data and such and comparing. Now this is kind of catch me all slide about bright sources and standards and PSFs. And so here's an image of a PSF right here. Here's the undistorted image, and here's the calibration image, which is shifted and added. So in this case, we shift and add, and it's only done on the standard images, but we shift and add the negative beams onto the positive beam. This only has a small effect in increasing the signal noise, much less so than you would think, so maybe only 15% and such. So it was more useful in the early days for standards at the long wavelengths because standard stars, although very bright, the short wavelengths really start dropping off around 30 microns. Now we've observed asteroids mostly for the 30 micron and longer wavelength data, so it's not much of an issue. So one thing people ask me when they look into error and issues, the biggest error, of course, is in the calibration. Our calibration is around 10%, perhaps sometimes higher in the log wavelength channels like that. So your major error when you're looking at data is going to be the calibration. If you look at the variance or the sigma plane and stuff, that will also have pixel-to-pixel error, but you're going to be dominated by your calibration error. Now you have both the final calibrated image, which is shift and add it, and you also have the undistorted image in case you don't want to have the shift and add, you can measure that. As you can see right here, these are typical array effects and very bright targets. You have this structure right here. Like I said, visibly it looks terrible, but it's actually a relatively small effect of only a few percent and such. So it doesn't affect the flux calibration and stuff. So, but it can be important when you're observing bright sources and faint sources, especially nebulosity. So when you're doing that, it's good to note which direction this is, and this will be in the direction of the ray. If you look in the ray direction, it'll be up and down and such. So for example, if you're observing some bright sources, some nebulosity, and some faint sources, you want to make sure you don't have a bright source and a faint source lined up so that you're basically affecting the faint source with this known structure and such. So this is very useful to know when you're observing both bright and faint and nebulous sources and stuff, is this effect. So also get asked a lot about PSF. How do you take a PSF? Or how do you measure PSF? Because unlike normal telescopes, you can observe the science over Texas and observe the point spread function or the standard star over California, which can have completely different weather systems and everything else and such. So in general, we previously just you've taken an average of all the standard stars during that whole cycle. You can use that. You can also check the maximum and minimum. You can look at all the standard stars and observe the full width F max, maximum, minimum to get a kind of error analysis and stuff. So, and that is that's proved useful, and we've many scientists been able to use that for deconvolution, and so the PSF does seem to work pretty well, even though it is taken in this odd way. So another issue is how we calculate filter offsets. Now this is the offsets between the filters. Here you'll see it in, this is the FORCAST file that we use it for, and we calculate this every cycle and stuff by using a pinhole mask. Because essentially the image on the array shifts by different filters. It can be largest at say 19 versus 31. So at 19 microns, if you're doing dichroic, right here, your star or object be at pixel 133.2, 130.7. But then at 37 microns, it'll be 118.5, 127.4. So that's a large shift. And you want to know, especially when you're doing observations in dichroic mode, two different filters, you want to know if there's an actual shift or not in your data, because it may indicate a temperature difference and stuff. So if it's hotter on one side and cooler on the other. So we try to measure this to make sure you don't have any errors in the shift and such. So You can see this in the Fiducia keyword. These are these values right here. Now this is before it is undistorted. This is in the raw data as far as pixels, which are still slightly rectangular before we undistort them into square pixels. So this goes to that data. So the Fiducia keyword records that number and then is transferred to CRPix 1 and 2, which is where we measure the bore site, where we rotate around and everything. So you have this data. This is typically accurate to less than 1 pixel, although this bore site can change over time. Sometimes during the beginning of the night, if we measure a bore site, usually the beginning of a series, we just keep it that way. But the beginning of the night to the end of the night, the mirror may cool and stuff. You may see slight shifts of a pixel or so as the bore site changes and such. It should change across the board to all filters, so it shouldn't create an extra offset, but the absolute bore site can change a little bit. Now, if you're very picky about knowing the difference between each filter and stuff, if you're looking for these offsets in temperature and stuff, I'd recommend taking a look at the standards to confirm the accuracy and error, because you can check the standards and see the relative offsets there to measure exactly what it was for that night and such, and if there's any differences. Like I said, this should be pretty accurate, should be pretty good. This is something we carefully work on, but just to note, this is a possible error and stuff. Older data had much worse issues with this than newer data. So, does anybody have any questions at this point? Okay. Well, next, let's talk about backgrounds and how to look at the background images. So, minnow instruments make great, well, I misspelled cloud. They're great cloud detectors too, but they're very good cloud detectors because, of course, water vapor affects us very strongly, and of course, clouds have large water vapor. So one way we look at that, we see variance in background counts between single files. So this may indicate other issues, large noise offsets, vignetting, or just variance in the background and stuff. So here's an example of some of the data. This is a standard star, alpha set, alpha boo, alpha tau. And you see this is the background level in counts for each of those 4 files. So on source, off source, on source, off source. And it doesn't matter if your source is on or off the source, the overall background is not going to be affected. So, of course, we run between about just background with nothing on it. It's around 2,000 counts to we get around saturation when it gets above 10,000, 12,000 counts and stuff. So we try to hit a sweet spot between 5 or 3 to 8,000 counts, 3 to 9,000 counts. So here's the counts by each frame. So in this case, 7,000, 7,000, 7,000, so like that. And this is the percentage difference between the maximum and minimum. So here, the largest difference. So this is only 51 counts difference between the maximum and minimum. So this is only a 0.66% difference between all those. So, and that is actually what we get. It's actually pretty stable between less than 1% most of the time. Perhaps jumping up to 1 or 2%. But you can see right here in this file, I'm getting a 4% difference in the background between those frames. That's indicating something's wrong. It doesn't take much, but it indicates something's wrong. Either some of the data is noisy, there's something wrong with the background, there's some clouds going on. The worst I've ever seen is like 7%. And that was like we were basically observing through fog and such. So it doesn't take more. Usually I flag data anything above 2% and stuff. So I notice 2-3% though still may be fine, but I always double check it and stuff, especially long wavelength filters, it's fine. Short wavelength filters tend to vary less. So, but this is how I check and how you can double check the data, especially older data before we did these checks in, is looking at the background level and the difference and stuff between the maximum and minimum. If it's over 4 or 5%, then you definitely have issues. So chances are we probably caught that during QA and such. But this just highlights some of the checks we do when we're looking at the data. Now, background variability sometimes is normal. This is the background at 19.7 microns in alpha boo. And see here, unfortunately, the bad pixel is coming in through there, the bad pixel paint fleck, which I'll talk about in a moment. But 19.7 micron tends to be slightly more variable than the other filters. You'll see these kind of dark waves and bright waves come through. This is just natural for 19.7 microns. We've tried changing the frame times, we've tried changing the nod times and stuff, but it just comes in and out. And so this is something to know when you're observing at 19.7 microns. If you're looking for very faint nebulous regions, you might want to go a little bit longer than even your signal noise estimates because you're going to have these large variations in background, relatively large and stuff, because this image is kind of blown out and such. But you'll see these kind of light and dark patches kind of come through. And the longer you observe, they kind of all even out and average out, and the background can be improved. But very short observations can have this structure. And as I said, it weakens over longer exposure. So just a heads up when you're observing anything at 19.7 microns. So this is another issue that can come up, although it doesn't come up often. It's come up before. This is basically when the nods are misaligned. This can happen whenever you do large chop and nod offsets and stuff. So especially when you're doing NMC mode, when you're chopping longer than 90 or 120 arc seconds, we certainly recommend going to C2 and C2 so you won't have this effect, or it will at least be diminished. So in this case, you can see in the final image, we just see an elongated source. In fact, this is kind of a pain in the butt to catch this one because this is actually naturally a double source, so it should be a little bit elongated and such. But if you look at the individual beams, this is not A, not B, and you look at the exact position, here's the double source. Here's the source here, and here it is shifted. So the nods are not quite lining on top of each other, so this is smearing out the data. So this doesn't happen very often, and sometimes it can be very hard to see because it's got to be bright enough to see in the individual nods to confirm and such. So as you can see, there's a large, strong radius offset here, so it's kind of hard to see unless the source is relatively bright. A hint, along with the same thing with chop nod smears, is if you see any elongations in the chop nod direction, be a little skeptical and double check the data and stuff. So I do checks for the data to confirm this, but if you're expecting not to see an extended source, and you see an extended source and it's in the chop nod direction, there's something to be aware of. There could have been some issue happen with the chop smear, which we had very early in data where the chop settle time was not set properly, or it could be this nod misalignment, which can happen. Like I said, if you have very large chop throws, this is something to be aware of. Like I said, we usually catch it, but just in case, there's something to be aware of. And whenever I say there's non-misalignment of data, this is what I'm talking about. Now, another issue, this is an 11.2 micron dichroic filter, not an 11.2 micron single filter. So only in dichroic mode is we see this ghost. So you might be able to see in the image right here, is it just shows a secondary source, like a second source. This is just a ghost. So it's only about a 1 to 2% level. Now, previously, we haven't used this filter that much, but we put it back into circulation now because 11.2 micron is a very wide filter relatively. It's the widest filter to show a wavelength, so it's 2.7 microns wide, compared to 11.1, which is only 0.95 microns wide. So it can be useful for detecting very faint sources with a much wider filter. And since the ghost is only a 1 to 2% effect, as long as you know about it, it can be very useful to use. Like I said, it's only in dichroic mode. So it can be useful if you're trying to measure a flux on a very faint source around 10 microns and stuff. It's probably better than 11.1 micron filter. So it can be useful for science as long as you're aware of this. And so this is something you can apply for if you need it. Now, here's another issue, vignetting. This is basically when the telescope is looking into part of the opening that we have and such. So this doesn't happen very often anymore. It happened a little bit in the earlier days of FORCAST. We catch it now much better. It's a relatively rare occurrence now. And it's pretty obvious. You see the effect very strongly. Here you can see 11 micron image. The short wavelength, what happens is the background just all flips out. You see all this structure and stuff just pop into the background. And you know right away something's wrong. For long wavelengths, it has a very interesting different effect. It kind of comes in as a faint bright or dark region along the edge of the array. And sometimes it's very hard to see the long wavelength data. It'll be very small effect, but you can see the 11.1 micron or the short wavelength data will be very much affected. So in that case, I usually make a note and set them both to usable or fail, depending on it. Well, usually usable because there may be something you can gain out of this and stuff. So, like I said, this is seen on telescope vignettes. The ZA range is 32 to 67 degrees, elevation of 58 to 23. So it's the higher elevation, which is the most stringent, 58 degrees at the very top of the opening and stuff. That's when we seem to have the most problems and such, because people like to observe at higher elevations. So, and sometimes it's unavoidable because the flight path can change. So sometimes the flight plan is fine, there'll be no vignetting, but due to strong winds or whatever, we push our flight plan a little bit, and so the first couple of files of a flight will be vignetted. And so usually I'll flag those and such. So, and if it's only a few files, I just will exclude them from the final coax. So this is useful for flight planning though, because the chop nod angle can make it worse. For example, if you're going up to top elevation and stuff like that, and you're chopping and nodding in the north direction, now you're actually moving even farther off into that direction, into the vignetting region and stuff. So chopping and knotting vertically or against the area of elevation could help there. So this is something to be aware of that we catch and stuff. But perhaps you've seen a comment or a vignetting, and you're like, what are you talking about? This is what I'm talking about. Now, an effect right now that we notice relatively recently when we start doing the mosaics level 4 data is distortion. Now, we have a distortion correction in FORCAST. It's an internal pinhole mirror or pinhole mask where we measure where the location of the point sources are versus, their ideal location and stuff. And so we do alter the data a little bit based on that. However, what we found is actually a large effect is due to the entrance window, which is a cesium iodide salt, which is kind of soft. And so over time can actually, I think, structurally distort slightly under vacuum pressure and such. So I think that's what we're seeing. And so across a whole array, the 3 arc-minute field of view basically of FORCAST, at the very edges, you can get about a 2 to 3 pixel offset or distortion if you're trying to line up with Spitzer images. This can be especially annoying in mosaics. Here's an example of the M17 mosaic of about 11 FORCAST field of views and stuff overlapping each other. And as I was putting this together, I noticed that some sources don't exactly line up with each other. So it can be very difficult to try to match things up and stuff. And so sometimes the mosaics are slightly more blurred than the individual data sets because I'm matching up data off by, about half a full with half max in some cases and such. So I also saw this in the Galactic Center, which was a beast to reduce because it was like 32 fields of view and such. So, but we are planning a future fix to try to measure the distortion through the window by putting it on the on basically what we call the TAS and stuff, and putting a distortion mask outside and taking data to try to measure the distortion from the window before we observe and such. So this is something we're working on, but something to be aware of and such that if you're matching this up against data for Spitzer and Wise and stuff, is that the very edges and stuff may not quite match up, and especially in large mosaics and stuff, you may have slight offsets and stuff. So be aware of that. Any questions? No? I'm going too fast by all this, that's all. This is an issue which has become more of a problem recently. This is the F0253, the 25.3 micron filter. We're noticing a possible light leak from shorter wavelengths and stuff. As you can see here, there's some slight fading structure, slight streaky structure on one side of the star. This is a standard star Alpha Boo and such. And one of the reasons we think it's light leak is we don't see this on the asteroids at the same wavelengths. So the asteroids are fine, so we think it's a shorter wavelength light leak coming in at a 25 micron filter. We're working to replace this filter, so we're going to try to order a new one and put that in and such. So it's relatively a small effect compared to calibration, so only a few percent effect and such. So, but it certainly can affect structure, and if you're looking for like a disk or something, or some misalignment of disk or some variability and stuff like that, this can affect it and such. So this is worth understanding. So, and this is something that's come up in the last 2 series, which is the bad pixel mask. Now, FORCAST has bad pixels at several points if we take account of pixel variations. The edge right here on the short wavelength is particularly bad right here. So something to know if you're doing mosaics, make sure you have a lot of good edge coverage right here because you're getting a lot of bad pixels. There's also some bad pixels at the top edge too. So, however, we noticed last cycle is this big blob right here. And this is what it is now. Before it was not, it was connected, but it's broken apart a little bit and some pieces is kind of flecked out and stuff. We think this is a paint fleck from inside the instrument and stuff. The instrument is getting up there in age and stuff, and we think perhaps the inner coating of the instrument may be flaking off a little bit and parts of it falling on the array. Now, this only affects the short wavelength array. We've had variation in bad pixel masks in the short wavelength array, and that's partly because of how FORCAST is designed. It's designed so that the short wavelength filter is kind of pointing up, or the short wavelength camera is kind of pointing up, or the long wavelength camera is kind of pointing down. So when it's jostled, move around, and under vacuum, stuff is likely to fall on top of the short wavelength camera and not on the long wavelength camera. So the long wave camera doesn't have much effect with this, like material, debris. The short wave camera does. So the pixel-pixel offsets are usually taken account of just by natural LS rewinds. Because remember, we're rotating the array and stuff as we're observing and such. So that naturally kind of dithers out pixel-to-pixel variations. But a big spot like this is required a dither, which is why in the last couple cycles we've required everybody to dither more. This has a small effect on the time to take the data. So, because each dither takes about 8 seconds to complete and stuff. So, but as long as you don't do lots and lots of dithers and stuff like that, we tend to do it in slower, so there's only a couple seconds. So it's only adding maybe 30 or 40 seconds to an observation and such. So it's just something to be aware of and such. So we noticed that last cycle we had plans to clean it and even possibly repaint the inside of FORCAST, but FORCAST was moved up a bit to observe just recently and such due to the Hawk Plus emergency. So Hawk didn't observe, so FORCAST observed, so that kind of took away our plans from opening the instrument and stuff and cleaning it out and doing some stuff. So so that's there for the time being. And like I said, dithering takes care of it. Spectra is fine unless it's very extended sources because the spectral go through this region. Our spectral bore sites tend to be a little bit higher in the array rather than the center of the array. We also have a bore site file for spectra. And so we tend to put spectra towards the top of the array, towards the top array a little bit, because this is the cleanest part of the array. You see, there's almost no bad pixels. There's some structure here towards the middle and the bottom. So we tend to put spectra towards the top of the array, so there's not much of an effect with bad pixels and stuff. So, but it's something to be aware of if you're looking at a very extended source and stuff. So. There we go. All right, and too early. So once again, I want to remind you, level 3 and level 4 in data ingestion. Level 3 data is finished and ingested in the DCS about 3 weeks, 15 business days after the last flight. It may take a day or two then to transfer and confirm and verify it at URSA before it shows up in URSA and such. So, and that's where you can get the data, check the QA comments and such. So, level 4 mosaics, which are both for mosaic fields. So if there's multiple fields, like in a very large area, or if you're just stacking data. For example, if you're observing a source very deeply and it's been over several flights and stuff. So I will stack the data together and put that, and that takes a little bit longer because that's a little bit more processing, a little bit more decision making as far as how to make the best science and stuff. So that usually is done afterwards, and then emails are sent out with level 4 data and such. So, and of course, once you get the level 3 data, you can start doing that yourselves. I just like to provide the mosaics and stack data for you as a convenience to make it a little easier. So, what else I want to say about mosaics? I think that's it. And now that's about 35 minutes, which is what I said. So, anybody has any questions or anything to say?
Thank you so much, James. That's going to be very helpful, and we'll post it on the website for anyone to watch. There was one question on the chat about aberration like coma. Anything like that on FORCAST?
Oh, we can get coma effects. It's especially bad in non-match chop mode if you have large chops. So the larger your chop, the more coma you can have. So anything beyond 60 arc seconds, you start getting a little bit of coma. Our limit is usually about 120 arc seconds and such. So if you want to, and so if you need to chop farther than that, I definitely recommend going to C2 and C2 mode. In fact, I think USpot, in case you put in more than 120 arc seconds, recommends you go to C2 and C2 mode, which unfortunately is less efficient because it takes longer to do, but you wipe out any coma, you wipe out any chopping and knotting onto any bright extended sources because you can go way off because the chop limit and C2 and C2 is like 420 arc seconds and stuff for most of the times. So you can chop and knot way off the data and not have to worry about that. So it is effect if you're, in NMC mode, if you're doing large chops and nods distances. So basically anything over 90 arc seconds, I'd be a little cautious about 90 to 100 arc seconds. So.
Thanks. And Kate has a question about whether there's any difference in the archival products between DCS and URSA.
No. They're exactly the same. So it's just transferred down and such. So it's just since we moved to URSA, there's just one extra step. So we put in a DCS first, and then it gets transferred to URSA, and so they have to take some confirmation to check everything and such. So
People can just unmute themselves for further questions or use the chat. Going to make 20 seconds of silence for question and then see what happens. And otherwise, we're going to finish here.
and like I said, if there's any other questions, like I said, or you think of something later, feel free to ask the help desk, or and they'll refer to me and stuff. So if there's any questions about the data, old data, new data, I've looked at everything since cycle 1, so I know all the issues and such. So
So have you seen all the products basically for FORCAST? I think it's fair to say.
pretty much, I was talking with Ed Chambers the other day, and it's pretty much I've seen every FORCAST imaging file that's ever been taken. So at some point, so not at least 95% of it. So
Okay, last chance for questions.
it says Eric is speaking, but I don't hear anything.
Oh, no,
Yeah.
no, I just unmuted. Sorry.
Oh, okay.
Okay. Okay, otherwise, well, then we'll stop here. And yes, we're always around the help desk, Sophia_help at sophia.usra.edu. And that's Steve and me behind the help desk, and we transfer things to James. So it's not going very far. Thank you, everyone. And thank you,
Thanks,
James.
James. Thanks, Ariel.
Thanks.